Thank you for joining us today. I'm Antonio Pietri, President and CEO of AspenTech. Although I'm not physically able to join you today in South Africa, I'm glad to join you via video conference. I hope all of you, your families, and employees are well, keeping safe, and healthy. I'd like to thank Blue ESP and 4Sight for the opportunity to share our vision for the self-optimizing plant and how artificial intelligence will transform how work is done and elevate operational agility and efficiency. Blue ESP is an essential part of our strategy to deliver the solutions required for digital transformation. I'm looking forward to being able to meet soon in person. For now, I'm glad for this opportunity to share our vision for the self-optimizing plant and how artificial intelligence will transform how work is done and elevate operational agility and efficiency. AspenTech introduced our asset optimization strategy in 2015. After decades of focusing on the design and operations of these assets, we felt there was another opportunity inside these plants, and we decided to take a look at the maintenance or reliability space. To our surprise, we found an opportunity because we saw that there was very little technology being used to predict equipment failure to improve the reliability of these assets. Of course, the convergence of Industry 4.0 capabilities such as artificial intelligence, high-performance computing, the cloud, has allowed for us to leverage a new set of technologies that, when combined with our design and operations capabilities, now allow us to look at the asset in a more holistic manner. And this is what we refer to as asset optimization, a comprehensive, holistic approach to achieving the highest possible financial return across the entire asset life cycle, and to do this in a safer, greener, longer, and faster manner. Today, we can look at the reliability of an asset and design these assets taking into account that reliability, optimizing the CapEx investment that goes into additional capacity in these assets, into the redundancy of these assets. We can look at how these assets are going to be operated and take into account the impact that that operation is going to have on the reliability of assets. So looking at this across the entire asset life cycle and creating a more optimum design, taking into account all aspects of the asset life cycle. Now, we know that the world is constantly changes and requirements are continuously changing. In Asia, we knew that companies like yours were facing a dichotomy. One where you had growing economies, improving standards of living, which really leads to more energy consumption, more plastic consumption. So in general, positive trends for the process industries. Equally, we were seeing society challenge the license to operate for your businesses through climate change regulation, through plastic waste concerns, and therefore the emergence of the circular economy. And all of this has been exacerbated by the pandemic. And so not only was the world changing, but the fact is that over the last number of months, the world has changed as a result of the pandemic and how that's transformed the supply-demand balances in the global economy. This has all led to what we refer to as a VUCA environment, and now an even more VUCA environment, an environment that is volatile, it's uncertain, it's complex, and it's ambiguous. Is that dichotomy that I refer to, where there's certainly growing economies with positive macro trends, but then the challenges from society. And now A lot of that has been flipped on its head because certainly there's a lot less demand for some of the products that you produce. But those regulations, those societal expectations on climate change and the circular economy are still there, which has created an even more challenging environment for your companies to operate in, and a more challenging environment for you to be successful going forward. On top of all of this, there's a new category of technologies, and those technologies that were announced in 2015 with the Industry 4.0, the cloud, artificial intelligence, robotics, virtual reality, edge connectivity. All these technologies are coming together and represent, in our opinion, either an opportunity or a challenge for your businesses, either enablers or disruptors, or both. And in our opinion, the fact is that these new technologies will be both. If they're embraced by companies and adopted, there will be enablers of competitive advantages. If they're ignored, they can end up being disruptors to your businesses. In this white paper by McKinsey, they identify that the early adopters of artificial intelligence will capture the majority of the cumulative free cash flow that will be generated from the implementation of these technologies. And those companies that are laggards in their adoption will actually fall even further behind on a free cash flow generation. So just a signal of the importance of these new capabilities in the marketplace. Equally, these new technologies represent a potential disruptor or opportunity for AspenTech, and we decided 3-4 years ago that we were going to embrace these capabilities and we're going to leverage them to deliver more innovation to the marketplace. So we started with a set of acquisitions in 2017. We've invested in growing our data science capabilities, where we now have groups of data scientists in AspenTech working with our chemical engineers, creating great innovation. And all in all, over the last 3-4 years, we've put to work close to $275 million in investments through acquisitions and organic investments to grow our capabilities. All of this is really set the stage or the foundation for what we are now referring to as industrial AI. And over the next few slides, I'll explain to you what we mean by that. Now, we refer to this slide as the candy store for data scientists because the fact is that machine learning capabilities, deep learning, artificial intelligence capabilities are very broad, and they're also in the public domain for the most part. Artificial intelligence algorithms started to be published many decades ago. They're in the public domain. Universities are doing a lot of research. Some of the basic technologies and most popular technologies today, such as TensorFlow from Google, can be downloaded from the internet. And all in all, there's no barrier to entry in the AI space today. The technology is not a barrier to entry like it's been in the past. And equally, this presents an opportunity, but also a challenge because anyone can be an AI company today. Now, we also have to understand that there's certain aspects to delivering AI capabilities in the marketplace, and Google published a white paper authored by some engineers there, where they basically argue that when creating ML systems, the actual ML code is only about 5% of the total source code that is required to deliver an ML application. The other 95% is the the capabilities to ingest, condition, structure data, how that application is going to be delivered, whether on the cloud or on the edge, and then creating that experience and that scalability. So from our standpoint, though, while we believe that's all correct, we also believe that in industrial space, in the industrial space, domain expertise plays an important role. So it's not only the machine learning code and the data collection capabilities, but also embedding domain expertise, the first principles, the physics, the chemistry, the math that relate the energy and mass balances, the process understanding, the equipment understanding, the operating constraints understanding, the process operations understanding, all that provides guardrails to AI to be safe to implement in industrial processes. So we also believe that it's not only the algorithms that are essential for ML systems, but also domain expertise and, of course, data. And it is in that context that we now refer to our applications as industrial AI applications that will certainly leverage large amounts of data, pervasive data, that will combine and use that data in the context of algorithms and to create the insights, how that data then is given context through domain expertise and industry experience in order to then derive the insights that are relevant for that industrial process that then provides the guidance and hopefully in a more automated manner so that it can be scaled by engineers as opposed to data scientists, since what we know there's a lot of in our companies is engineers and not data scientists. So all of this is the foundation for what we refer to as a new generation of solutions. AspenTech is taking our historical knowledge and expertise in first principles, those products that you've grown to love, HYSYS, Aspen Plus, our APC technology, DMC3, our refinery and ethylene planning technologies, PIMS-AO, and we are enhancing those capabilities now with artificial intelligence. So what you will start seeing from AspenTech is a new generation of products that will refer to as hybrid products that will combine or will have hybrid modeling capabilities. In the case of HYSYS and Aspen Plus, you're going to see capabilities in these products where artificial intelligence will be embedded within the first principles in order to improve the predictive capability, the accuracy of those predictions. For example, in the case of highly nonlinear processes that are very difficult to model using first principles, we can now use data, the data coming out of these processes, nonlinear processes, to create empirical models that can then be embedded as machine learning objects in the first principle models. We'll be able to do the inverse as well, have pure empirical models where we'll be able to embed first principle objects into those models. This is very exciting. It's something we've been researching for 2-3 years. It's been one of our most successful innovation clubs and beta testing clubs with our customers in our history, and we're very excited to put these in the market. Now, we're also looking to help you in accelerating the design of these assets, sort of optimizing the time that it takes to design of these assets. We're introducing multi-case capabilities, and instead of relying on only a few use cases to come up with a design for an asset, where perhaps we miss some of the key features that would help optimize the CapEx required to build that asset, you are now going to be able to run thousands of scenarios using additional cores in your desktop computer or cores using high-performance computing on the cloud to run many more scenarios in less time in order to find that optimum design, and will provide you with enhanced capabilities, both visualization and through analysis using AI in order to determine the optimum design point for those designs going forward. This is something very exciting that will be available soon in a future release. We're also working on deep learning APC. We know that historically the implementation, the design, configuration, and implementation of a multivariable controller has been a manually intensive process. It's relied on the expertise of a process engineer. We're working on automating a lot of those manual processes. We're working on automating a lot of that expertise that was coming from a process expert by leveraging machine learning capabilities, deep learning capabilities, so that in the design of a multivariable controller, we can use deep learning expertise to identify those variables in the process that are correlated, the manipulated and controlled variables, by looking at P&ID charts and identifying those relationships. We're going to try to automate the configuration of those controllers, the development of the model relationships between the variables using historical data or simulation data, and machine learning capabilities to derive those models, the ability to embed nonlinear models in the control matrix, also using machine learning capabilities to model highly nonlinear processes, and eventually implement those controllers using the adaptive capabilities that today exist in the MC3. This is a very exciting development because going forward will lower the barrier to implement multivariable controllers, will automate a lot of the knowledge and democratize more and more the implementation of APC controllers. Equally, cognitive guidance for planning. The fact is that a planner in a refinery or an ethylene plant creates and executes many of these plans over the years, leading to hundreds or thousands of plans being executed. Well, we're going to be able to sift through those historical plans and the outcomes achieved and learn from the decisions that were made to create those plans in order to create a learning system that eventually will be a cognitive guidance system for a future planner, so that as the planner is working to create a plan based on a specific scenario, it could be summer mode operation or winter mode, the technology will guide the planner in the decisions that he or she has to make to create that plan. The technology will be able to check whether some of the decisions made on the design of that plan were the right decisions, and therefore create a more automated process for planning, and lower the barrier of expertise also required to create a plan in a refinery or chemical plant as well. As part of these cognitive capabilities, we are creating in our engineering products in-context guidance. Again, we can learn from the decisions made in the design of process units or assets from historical designs, and then use that knowledge and put it into automated, and then be able to provide the design engineer, the process engineer that is creating new designs in the future, give guidance to that engineer, be able to guide the engineer in the right decisions based on that historical learning. In addition, we're going to include e-learning in the product so that there can be a greater increase in the productivity of engineers, so that engineers can learn as they are using the products without having to leave the product itself, and that will be part of what you'll see in future releases as well. Now, all of these will lead to an environment where we'll be able to put a lot more models online by creating these hybrid models that combine first principles and AI, or pure empirical data models. So you can see a world where now a plant will be much more highly monitored by small engineering models online. You can also see a world where we're now implementing smaller APC controllers that are designed and configured through these deep learning capabilities. So edge computing will become a requirement. And in order to deploy a lot of these models, in order to ingest a lot of the data that is required to be consumed by the AI capabilities in these models, and therefore how do we deliver them? And that'll be through edge computing capabilities, and that could be either on a computer at the edge on premise or on the cloud as well. So in that context, AspenTech, through the number of acquisitions we've made in the last few years, we've created a new solution that we refer to as the AIoT Hub, the AspenTech AIoT Hub, which is the infrastructure that will be required to deliver this new generation of products and provide the connectivity, the cloud capabilities, the infrastructure to deliver these hybrid applications, and then the visualization and the collaborative workflow to be able to share the insights that are created by the applications that are running on top of this industrial AI infrastructure. So all of this really sets the stage for our vision in AspenTech and is what we refer to as delivering the future. If you go back 30, 40 years, the fact is that 40 years ago, a lot of the processes in industrial plants were manual processes, paper-based processes. Of course, with the advent of electronics, a lot of those paper or manual processes became electronic processes. And today, most of our customers are between phases 2 and 3 in that journey to really the smart enterprise, where some customers are already doing single unit optimization or have planning capabilities but not scheduling. But there are some customers that already implemented planning scheduling are doing multi-unit capabilities. Well, the goal is to get to the smart enterprise, and it will be a set of solutions that combine AI and first principle capabilities, domain knowledge, to drive continuous improvement. And AspenTech is set ourselves as a vision to deliver that smart enterprise, and what we call the self-optimizing plant is a plant that is safer to operate, that is more sustainable, that is more reliable, and therefore is more profitable over time, is a plant that maximizes and sustains value. So what do we mean by that? Because it is as important to say what the self-optimizing plant will be as it is to say what it will not be. But we envision the self-optimizing plant to be one that is self-learning, self-adapting, self-sustaining. Is a set of technologies and processes that will work together to predict future state and predict or automate action. It will use pervasive data. It will automate decision making. It will prompt for actions to be taken when necessary. Yeah, so the self-learning plant is one that will utilize data, whether it's historical data or simulation data or real-time data from the environment, from systems, to get smarter and increase the accuracy and scope of predictions. As operating conditions changes, machine learning capabilities, deep learning capabilities understand how those changes drive the process, drive the production targets, and therefore it gets smarter over time. The self-adapting plant will be one that, as it sees changes, for example, if a thunderstorm rolls through, we know that typically that drops the ambient temperature, which impacts the operating conditions in the plant. So the technology will learn what these changes mean to the operating of the plant and will incorporate that in order to always meet targets. So it's adapting through deep learning capabilities that are embedded in the technology in order to meet those objectives. The self-sustaining plant will be a plant that is detecting anomalies, is detecting when equipment is going to fail, is detecting process degradation before it actually happens, and is triggering for actions to improve the longevity, maybe changes the operating targets of a plant in order to extend the life of an asset, or it changes operating conditions in order to prevent process degradation. A self-sustaining plant is one that maximizes uptime, maximizes reliability. So we know that these plants are not in a vacuum. They're part of an ecosystem. They're part of an enterprise. And so the self-optimizing plant will be one where is also balancing the supply and demand balance across multiple plants for maximum results. It's optimizing across multiple plants, and it's always looking to answer the questions of what's happening now and what do I do next. And in that context is a solution that is continuously delivering insights to improve operations, automatically sifting through information, through the noise, to provide transparency and guidance on what matters most. It's executing autonomously, is requesting human approval when necessary, or is recommending for human intervention based on the risk level. We also expect that the self-optimizing plant will have a highly immersive user experience. One will have a 3D representation of that plant, where an operator and engineer will be able to see all the operating parameters that are current in that plant, the operating limits, what targets are being set by the technology, what targets are being changed, what approvals are being requested by the technology, perhaps changing a limit on a unit, what alerts are being issued about a potential failure in an equipment or process degradation, or even perhaps opportunities for a revamp of a unit based on the learning that's happened in the technology over time. Very immersive experience, a 3D type experience that would complement what we refer to as the self-optimizing plant. Now, the self-optimizing plant, of course, will integrate a performance engineering component, a production optimization, the autonomous reliability, and the value chain optimization, the supply and demand balance, which is what will drive the operation of the plant. And therefore, there will be an autonomous performance engineering component to it, one that where a lot of those services that are normally performed by an engineering services group have been automated through models online, an autonomous production optimization process where we close the loop from planning down to optimization and control and back, and an autonomous reliability and maintenance process where the technology is recommending for changes in operations in order to extend the life of an asset. And all that in the context of the information that is relevant in the supply chain that needs to be taken into account to drive the operation of this plant. So it's a solution that will rely on industrial AI, will include collaborative workflows, an immersive user experience, and will deliver it using the Aspen AIoT solution going forward. And we know it's not only one plant, it's a set of plants, therefore we have to optimize across these three plants on the value chain. So this is what we mean by the smart enterprise. It will be a journey that will be delivered over time, but one that we believe will transform the process industries again, like we helped transform the industries over the last 35, 40 years. Thank you.